Hi, I'm Kingsley Horton from Acclima. In this presentation, I'm going to introduce you to an exciting new soil water content measuring technology. It's a fully integrated time domain reflectometer developed by Scott Anderson, the President and CEO of Acclima Incorporated. This new approach is a major breakthrough in TDR and is highly accurate, stable, and credible in making soil water content measurements. I will also show through theory and empirical data how it overcomes the errors caused by soil electrical conductivity, a major weakness in currently available non-TDR or non-TDT sensors. Nearly all soil water content measuring devices are based on the measurement of the dielectric constant, or permittivity of the soil, which is dominated by water content. By measuring permittivity accurately, it's then possible to come up with an accurate measurement of water content through the top equation, or a dielectric mixing model. Permittivity manifests itself in two distinctly different but observable principles. The first is Gauss's law, which relates electronic charge to electric field. Numerous soil moisture measurement devices are on the market that use or are influenced by Gauss's law. Examples are LC or RC oscillators, standing wave or transmission line oscillators, and various impedance measuring devices. The common basis and also common weakness of all these is that they are based on current and voltage measurements and relationships that are associated with various clever electrode configurations placed in the soil. They can be classed as Gaussian sensors because they approximate soil permittivity from Gauss's law, which relates electron charge or charge movement, which is current, to electric field, which is related to voltage. Permittivity is then approximated as a proportionality constant relating charge movement to alternating field magnitude. Even though these devices use widely differing electronic circuits and sensor geometries, they are all dependent upon or influenced by Gauss's law, in that their derivation of permittivity is based on current and voltage amplitude and phase relationships. Various clever electrode geometries have been designed along with various electronic circuits to sense permittivity as a function of current and voltage relationships in the electrodes. All soil moisture sensors that sense permittivity through current and voltage measurements are Gaussian sensors. They generally all work well in soils that are free from salts and other ionized substances. It's important to note that the E field term in Gauss's law is not just a voltage. It's the vector integration of the whole electric field and has a geometrical component associated with it. In very low conductivity soils, the E field can be assumed to be a constant. Likewise, this charge term is the total charge within the total electric field. Again, in low conductivity soils, the total charge can be assumed to be represented by the current flow in the electrodes. The problem in applying Gauss's law is that it requires an accounting of all the electronic charge or currents within the influence of the electric field. Soil ions outside the sensor body are also electronic charges. They are not taken into account in the measurements made by these devices. Neither is the attenuation and distortion to the electric field caused by these external ions. If a permittivity measuring system is dependent upon monitoring charge or charge movement or voltage amplitudes, and if unmeasurable charge and distorted fields are present in the system, then Gauss's law becomes a problem rather than a means to a measurement. Sensors that are based on or impacted by Gauss's law report substantial permittivity errors when external soil ions are present. The second principle wherein permittivity is manifest is in electromagnetic wave propagation. EM propagation is based in Ampere's law and Faraday's law. By combining these two laws, we can derive this astoundingly simple relationship, which is EM wave propagation is a function only of permittivity and magnetic permeability. Permeability is a constant in soils. Permittivity can then be derived by measuring the propagation time of an electromagnetic wave through the soil. This measurement is not dependent upon field geometry and is not a measurement of any current, voltage, charge, or field. It is only a time measurement. There is a precaution here. As EM waves pass through soils, they become attenuated by soil ions and are distorted by complex permittivity components in various soils. If currents, voltages, charges, or fields are used in the time measurement, then Gauss's law taints the measurement and it becomes subject to errors introduced by soil conductivity. In order to avoid the impact of Gauss's law, it becomes necessary to digitize the waveform at very high resolution and then use digital signal processing algorithms to extract the temporal properties of the wave, independent of magnitude. Remember, Gauss's law is associated with current and voltage relationships. The propagation equation is time only. Without these added waveform digitizing and signal processing steps, the use of the propagation equation to derive permittivity would yield errors similar to those associated with Gauss's law. Examples of soil moisture sensors that use this principle are true time domain reflectometers and true time domain transmissometers. I use the term true because there are devices on the market that purport to be time domain based, but are actually Gaussian sensors in sheep's clothing. Here is a typical true TDR setup. An expensive TDR console houses three essential elements: a step function generator, a precision time base, and a waveform digitizer. The TDR console is coupled to a waveguide through a coax cable. This cable facilitates separating the console from the waveguide for practical installation purposes. But it also acts as a low-pass filter and removes much of the gigahertz spectral content out of the measurement, thus reducing resolution and possibly hiding important medium characteristics. Then, in addition to these, we need some software and a PC to interpret the waveform and derive permittivity and moisture content from it. We can improve this picture. Let's take the simple necessary elements out of this box. Then we can throw away this other expensive stuff. Since these elements are small and can be placed in a small waterproof package, let's couple them directly with the waveguide. Then we can throw away the bandwidth limiting cable. Let's also throw out the PC and the waveform interpretive software. Here's what we get: an integrated true time domain reflectometer. This convenient little TDR does everything that the more expensive conventional TDRs do, but has these additional advantages. The waveform analysis is built in. The device reports a multitude of parameters including water content, permittivity, temperature, propagation time, and so forth. It can even download waveforms for those of you who wish to learn more about the soil structure or the dynamics of its water content. The waveform capture, analysis, and data reporting occurs in less than 1 second. With no coupling cable, the waveform bandwidth is unconstrained. The device is temperature compensated. It provides accurate EC readings directly from its waveguide electrodes. It is waterproof and rugged and designed for long-term use in the soil. And it's a small fraction of the cost of a conventional TDR system. Here's a summary of its performance. The step function applied to the soil has a rise time of 100 picoseconds, providing a very wide spectral content for the measurement of soil properties. There is no cable to disrupt wide bandwidth, and the receiver input has a bandwidth of 8 gigahertz. The digitizing resolution is 5 picoseconds, implying an effective digitizing rate of 200 billion samples per second. The reported permittivity and water content readings are immune to EC up to the point at which the signal is attenuated to where it can no longer be received. The device has an SDI-12 interface and runs on any voltage between 5 and 15 volts, drawing 10 microamps in its idle state. The active state current draw is 250 milliamps for 800 milliseconds. These are actual, untouched, spontaneous waveforms and associated readings from the device in various saline water solutions. Note that the sensor reports fractional water content from 0 to 1, not as 0 to 1/2 as with most other sensors. Note the incident wave here at the left with its 100 picosecond rise time. Following that is an impedance mismatch area where the electronics connect to the waveguide and the whole of that connection is inside the enclosure. At this point, the wave hits the water. As you can see, with distilled water, there is no attenuation of the wave. The reflected wave occurs at this point, and this particular TDR reported a fractional volumetric water content of 0.994. As we add salt to the water, we can see a drooping attenuation of the incident wave and the associated attenuation of the reflected wave. If we were dependent upon waveform amplitudes rather than timing, we would be in serious error trouble. Note that in these saltier solutions, the time of occurrence of the reflected wave is becoming difficult to see with the naked eye. But there is an inflection point associated with the reflected wave that can be accurately recovered from all these waveforms using appropriate digital signal processing algorithms. In these saline waveforms, you can see the superiority of the time domain sensors over Gaussian sensors. Note that the propagation time of the reflected wave is not affected by the medium conductivity, even though the amplitude of the wave is severely attenuated. Notice that the water content reporting is accurate to within 1 percentage point in all these solutions from 0 to 4 decisiemens per meter EC. At 5 decisiemens per meter, the attenuation of the wave becomes significant enough so as to cause a slightly larger error in reporting. Here are some untouched waveforms and readings from soil samples wetted with water of varying degrees of salt content. The gravimetric readings shown were made by carefully weighing the added water to dry silt of known density and residual water content. The sensor readings shown are those reported by the sensor. Note that the reflected wave from the dry soil sample has an abrupt inflection point. Because of the low water content, the reflected wave bandwidth is very high. You would not see such detail if a coax cable were involved. Note the accuracy of the readings where the water EC was 0.35, 5, and 10 decisiemens per meter. At 16 decisiemens per meter, the sensor underestimated the water content by about 1 percentage point. But this is not due to any flaw in the underlying principle, but rather is caused by the fact that the reflected wave is nearly dissipated by the attenuation from the soil ions. The data from the previous slides came from a device like this. It's a fully integrated time domain reflectometer soil water measuring device with a 15 centimeter 3-element waveguide. Thank you for listening to our presentation on Acclima's new True TDR technology. If you'd like more information on the status of this and other devices using this technology, you may contact us at sales@acclima.com.